Welcome back, everyone. So we are jumping into Chapter 2. So Chapter 2 is all about differentiation, and in particular, this operation that we call the derivative. And so we're going to start by actually going back to our 1.1, 1.2 notes, where we discussed that tangent line problem at the very start. And what we're going to do is we're going to generalize it so that we can actually get a function that we call the derivative function. That's going to be one of the main tools that we use for this entire course. So for example, that we had from that first set of notes was we had curve 9 minus x squared, I believe. Yeah, so it was 9 minus x squared. And we were interested in calculating the slope at 1. So we took the limit of the secant line between that point, and so we picked points that were really close, like 0.5. We picked those 2 points, and we drew the secant line, and we said, okay, well, the slope is close, but it would be even better if, say, we did 0.9 to 1, right? And we got better and better approximations of the tangent at that point, and the importance of the tangent line is that the tangent line has the same slope or rate of change as the parabola at x equals 1. So that approximation that we did gave us the exact slope at that point, which I think was -2 for that particular curve. And so that was the key, was that we could get the exact same slope. Because, you know, if I have a line, it's easy to calculate the slope of a line. We just draw our little slope triangle, do rise over run. But for curved objects, or things moving along a curved path, it's much harder to figure out what the speed or velocity is that they're moving at. So what we're going to do now is we're going to generalize this process. So we're going to get rid of this for a moment, and we'll redraw. And we're going to end up with what we call the derivative function. So let's go ahead and start over. And we're going to note we're going to be dealing with the same curve here, 9 minus x squared, let's say. But actually, we're going to get rid of that as well, because I don't want to refer to a specific type of function necessarily. And we're going to just generalize. So we're going to imagine that we have some function, nice continuous function, that we're going to call f of x. So here's y equals f of x. And what we're going to do is we're going to pick a location, which we'll call x. Zoom in a bit here. And what I want to do is I want to figure out what is the slope at that location. So in order to do that, I'm going to do that same limiting process that we did on the first day of the notes. So we're going to move some distance away. Now I can move to the right or to the left. Doesn't matter which way we do it, because in either case we're going to get the same slope variation. So if I pick a point to the right, I'm going to call it x plus h. So I'm going to add h. So then just note h is this distance here. Oops. Or again, I could subtract h if I wanted to. And that would still be the same distance h. Now note, by calling it h, I can make that distance as small or as far as I want it to be. So for our first picture here, we're just going to draw h a little bit further away, right? And again, what we could do is we could create a line, a secant line, to approximate the slope at x. So again, whatever the slope is here, that's going to be our approximation. of the slope at x. So let's make a quick note over here then. So the slope is going to equal the secant slope is going to equal, well, let's label a little bit more here. So we'll note, this is f of x, wherever x is located. And then this is f of x plus h. So we've got our y values. So if we labeled our coordinates here, we've got x comma f of x. And we've got x plus h comma f of x plus h. So we've got those 2 points. So if we find the secant slope, it's just going to be rise over run, or the difference in the y coordinates over the difference in the x coordinates. So that's going to be f of x plus h minus f of x all over x plus h minus x. Right, so that would be our secant slope. And we'll notice a convenient cancellation here. So what we end up with is something that you've all seen before. That f of x plus h minus f of x over h, which is what we call the difference quotient. But that's our secant slope. So what we're going to do then is to find the actual slope is we're going to shrink this distance down. Right? So we're going to let h go to 0. And as I shrink that down, that secant slope, which is the approximation, will become the exact slope. So in other words, the slope of the tangent, which is also equal to the slope of f of x, is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. So the slope of the tangent line, which is also the slope of f of x, is equal to the limit as h goes to 0 of f of x plus h minus f of x over h as h goes to 0. And this is called the derivative function. And what we call this is f prime of x. So this is going to be our first major definition. And just note, we could do the same process if we called this a, and we move some distance x away. So if I wanted to find the slope at a, so I want to know the specific slope. Let's call this f of x. So if I want it at a specific point, call it a, it would be the same sort of limit, but what I would be doing is shrinking the distance of x from a as x approaches a. So this would be as x goes to a. And what we would get is the limit as x approaches a with f of x minus f of a all over x minus a. So similar process, only now we're doing it at a specific point. So the key difference here is we're approaching the actual domain value we're interested in. And so this would be the specific slope at that value a. So this is another definition. So note, same essential proof or style of proof method, but the difference is in what it describes. So this is the slope of f at any value x equals a. So this is at a point. So this is the specific slope at a point. Whereas up above here, we have no reference to a specific point. We've just called our generic location x and then the distance away x plus h. This is the slope of f at any value in the domain. So, two different definitions that are really describing the same thing. And so we're going to use both. I would say that the most important one is this, because it gives you the slope at any value. But you've already dealt with this limit down here. So if you remember back in the, I believe, 1.3 homework, you were given an object that was dropped off the top of a building, like 200 feet or 150 feet. And they gave you this velocity limit. They said the velocity is the change in position from x to a over x minus a, etc. So that was really computing the specific slope at that value a. But note, these are both describing the same thing. These are both describing slopes. It's just the context is different for each one. One is generalized as a function. So f prime of x is itself a function. Whereas this value, f prime of a, is going to be a number that represents the slope of the function at that point. Right? So one is a function, one is a number. And this will be a common theme when we get to integration, the second major topic of calculus in chapter 4, where we will define that integral as a function or the integral as a value. So going back here, we will just formalize our definition in the notes here. So our first definition is the definition at a point. So f prime of a is the limit as x approaches a, f of x minus f of a all over x minus a. So this represents the slope of f of x slope of the function at any point a in the domain, and also the rate of change of f. And the reason why I put that is because we're going to be interchanging slope and rate of change. So slope and rate of change are going to be synonymous ways that we describe the function itself at that point. And in application, this is going to refer to typically velocity. Okay. So now I'm going to actually jump ahead, and we're going to put our second definition here, which we already worked out and described. So that's going to be the limit as h goes to 0 of f of x plus h minus f of x all over h. And again, provided that the limit exists, of course, so we can have undefined slopes if we are vertical at a point, but then we will not be a function, so we will fail the definition of function. Okay. So we've got an example here. Find the slope of the graph y equals 2x squared plus 1 at the point 2 comma 9. So note the point 2 comma 9 is a point on the function. So we're going to get situations where we have points not on our function. But the point 2, 9, if you plug in 2, you'll get 4 times 2 plus 1, which is 9. So that's important for the moment. So we want to find the slope. So we have two options. We can do the slope function or the slope at a point. So if we do, so we'll call this y equals f of x. So f prime of x would equal the limit as h goes to 0 of f of x plus h minus f of x all over h, or we could do f prime of 2 is equal to the limit as x approaches 2 of f of x minus f of 2 all over x minus 2. I'll put a little dividing line here. Okay, so if we want to use the first definition, we're going to get the limit as x approaches h. So it's going to be 2 times x plus h squared minus 2x squared all over h. And if we use the second definition, it's going to equal the limit as x goes to 2 of 2x squared plus 1. Oh, whoops, I forgot the plus 1. Minus, we know that f of 2 is equal to 9 all over x minus 2. So we go back and fix this one. Now, it's actually not going to matter in the end, but it does matter to begin with. So that's 2. So there's my f of x plus h minus 2x squared plus 1. You'll notice, though, that the plus 1s are going to cancel when we distribute. So we'll get that this equals the limit as h goes to 0. So if I distribute out x plus h squared, it's going to be x squared plus 2xh plus h squared, all times 2. So you're going to get 2x squared plus 4xh plus h squared minus 2x squared all over h. And again, we'll get some nice cancellation here, so those will cancel. We'll move down here and get the limit. H goes to 0. I can factor out an h from 4xh and h squared. Oop. And so we'll get the limit as h goes to 0, 4x plus h. Let h equal 0, and we get 4x. Okay. So that would mean at 2, right? So this is f prime of x. So then f prime of 2 is going to equal 4 times 2, which is 8. Okay, so that looks like it's going to be the slope. We want to find the slope with the graph only, so we could also find the tangent line at that point if we wanted to, but we don't need to yet. So f prime of 2 is 8. So let's check this in limit and see what we get. So just note off to the side here, this is going to equal the limit. So x goes to 2 of 2x squared minus 8 all over x minus 2. And then again, we'll do a little bit of factoring. So limit as x goes to 2 of, we can factor out the 2, we'll have x squared minus 4, which is going to factor as a difference of squares. So let's go ahead and cancel those two. And with the limit as x goes to 2, 2 times x plus 2. Plug in 2, you get 2 times 4, which is 8. So it works the same way. However, note, if we were finding more slopes, this would be more useful. But in general, this is going to give you essentially the same value that you're looking for. And again, if I wanted to find the tangent line, to our curve at 2, 9, that would be y minus 9 equals 8 times x minus 2. Boom. Because we're going to need to know the point and the slope, point-slope form is definitely going to be your friend. Point-slope form is much easier. You could distribute this out, but I'm going to highly, highly recommend using that point-slope form because this is much easier to work out than trying to figure out what b is in a lot of cases, because b could be really, really messy. All right. So we've defined the derivative two ways. One as a function in general, one as a value at a point. And what it means is the slope or rate of change of that function. So it is the slope or rate of change of the function at a point or at a given domain value. This space up here is actually for that second proof that I ran through pretty quickly. We'll spend a little bit more time on it in class. And so we're going to get some different notation and then work on some additional examples next time. But until then, if you have questions, definitely send me an email or drop by during the office hours. But otherwise,